All right. Hello. Can you hear me?
Yes.
Thank you. Okay. All right. We'll get started in about a minute and a half, folks. All right. It's 12:30. We'll get started. So we were talking last time about cyclic acetals and ketals, and I discussed two reactions. One was the adding of the diol, which is a compound like this. It's got two OH groups on the same molecule, to a ketone or aldehyde to produce what was either a acetal or ketal, a cyclic acetal or ketal. The other reaction we dealt with was the reverse reaction, which was taking that cyclic acetal or ketal, treating it with H2O and H+, and then turning it back into the ketone from whence it came, and the diol as well. So in this vein, we can talk about protecting groups. Now, these cyclic acetals are very popular protecting groups when we're dealing with things that have C double bond O's in them, and we don't want that C double bond O to be damaged by a reaction. So if you've got a compound like the one I have here with this C double bond O and this CBr, there are actually two possible ways that a nucleophile could interact with that compound. The nucleophile could attack the delta plus on the C double bond O, or it could attack the delta plus that's on the C that's connected to the bromine. So the question would be, how might you protect one of those groups, namely the C double bond O, from attack from the nucleophile? So what you can do is you can put on a protecting group, which is the cyclic acetal. So you can see by adding the cyclic acetal, then we can attack the compound with the nucleophile. It will only attack the C with the bromine on it, and then the protecting group can be removed with H3O plus in using the reactions that we just talked about. Now, when choosing a protecting group, they must be easy to put on. So this group must be easy to put on, and cyclic acetals are typically fairly easy to prepare. They must be stable under the reaction conditions, and they must be easy to remove. So under the basic conditions with the negative charge on the nucleophile, these things can survive, but as soon as they're put into acid, they tend to fall apart back into the ketone from which they were made. So these particular cyclic acetals are a good choice as a protecting group. Does anybody have any questions so far? Okay. So we're going to look at some other reactions, and these are reactions that hopefully you've seen. You saw them back in Organic 1. And the first one, let's get rid of that. The first one is the Grignard reaction. Now, Grignard reactions are common reactions for putting carbons together or adding carbons to a certain chain. And if you've got a C double bond O, then it's eligible to be added to a chain that could come from a Grignard reagent. When we're dealing with Grignard reagents, let's first of all look at what a Grignard reagent is. A Grignard reagent is this compound that's got the MgBr in it. And these are typically made by what's called an insertion reaction. So we can take the alkyl halide, which is this compound here that's got the bromine on it. We can add magnesium, or actually stir it into magnesium turnings. And then what happens is that let's have a look. When you've got the bromine attached to it, then you've got a delta plus on the C that's connected to the bromine. And then when we add magnesium to it, it turns into this Grignard reagent. And you'll notice that now, because the metal is delta plus, it means that whatever it's attached to, will be delta minus. So what's happened here effectively is that the C, this is the same C by the way, has changed from a delta plus to a delta minus. The Germans call that Umpelung, which is a terminology that means a reversal in charge. So this is very useful because what it enables us to do is to prepare compounds that effectively have a negative charge on the carbon atom. Whenever I see a Grignard reagent, what I do is I take the MgBr off and I effectively put a negative charge on the C where the Mg was connected. So you can see that that's what I've done in each of these instances. You take off the MgBr, the negative charge is on the C. The MgBr is on the C, and the negative charge is on the C. And you can see that in each of these. You've got to be a little bit careful here because there is no carbon at this point. The carbon is here, where I'm pointing this arrow to. That's where the C is. So you've got to be careful about that, and that's the C that gets the negative charge, the one that's connected to the Mg. Does anybody have any questions so far? All right, when dealing with the mechanism then, what we do is we take note of the fact that the C double bond O has a polarity associated with it. It's going to be delta minus on the O and delta plus on the C. That means that anything that's attacking it that's negative is going to attack the C that has the delta plus, which is why when I take the Grignard reagent and I take the MgBr off, I put a negative charge on the C, and then I know that what's going to happen is I'm going to form a new bond between the C that has the negative charge and the C double bond O. So this here is the new bond. I'll see if I can change the color of it. There we go. So that bond there is new, that red bond. And it's due to the negative charge on the C having two electrons that are being used to form a bond between the C that has the negative charge and the C that was part of the C double bond O. Then the electrons jump up onto the O because we can't have 5 bonds on that oxygen there. And now the oxygen has the negative charge that the C used to have. Does anybody have any questions? In the last step, we see the O negative add on to an H plus that's in a second step. And again, we end up getting this product here that it's got the new bond here that I'm showing where the arrow is. But one other thing about this one. Now notice how it's a 1-2 process. What does this indicate? It indicates that we're using the Grignard reagent first and then putting the H plus in a second step. This is not meant to be saying, well, you know, we use the H plus first or we have the choice of what to use. We don't, because the steps are actually laid out for us. So the Grignard reagent has to be used first and then the H plus can be used second. That's not always true. When we have no 1 or 2 here, then we can make an informed choice about which one to use first. Generally, it's a charged one. And then that gives us that'll lead us to our product. Does anybody have any questions? So I have this laid out here. Sometimes what happens is when people do this mechanism, they ignore the new bond. And what they'll do is they'll just basically fuse the C that had the negative charge and the C that had the C double bond O, which leads to a compound that has fewer carbons than what we started with. So that's not really the situation we're looking for. So that's just something to be careful of. Does anybody have any questions? So depending upon what you start with, you can get different kinds of alcohols. And when you're expressing these Grignard reactions, you can express them in 2 ways. We can always have the aldehyde or ketone at the beginning and then put the Grignard reagent next to the 1 on top of the arrow. But there's really no difference between putting the Grignard reagent where the aldehyde is and putting the aldehyde where the Grignard reagent is. Effectively, it's the first step, and it's like I've got here. If you want to make scrambled eggs, you can add milk to eggs or eggs to milk. It doesn't really matter. So the first step is interchangeable, is what I'm trying to say there. So these things above the arrow here were the things that were in front of the arrow in the first example. That's why I've got the or here. Now you'll notice that depending upon the kind of aldehyde or ketone that we use, we're going to end up with a different kind of alcohol. So you'll notice if we use formaldehyde, which has 2 hydrogens attached to the C, it's a very specific kind of compound. The compound we end up with is a primary alcohol, something where the OH is on the end of a chain. If we use any other aldehyde, the product will be a secondary alcohol, where the OH is in the middle of a chain. And if we use a ketone, then the product is a tertiary alcohol, which has 3 groups connected to the C with the OH. Do you have to know any of this? Not really, no, but I'm just pointing this out. If you want a specific kind of alcohol, then you can use different kinds of aldehydes or ketones in order to get to that point. Does anybody have any questions? Okay. The next reaction we're going to look at is called reduction. And this is another one you would have hopefully seen in Organic 1. And you can see that the process consists of NaBH4 and H+. And you'll notice again it's a 1 and a 2 step. The NaBH4, if we look at it, consists of Na plus and then BH4 minus. But if you look at where B is on the periodic table, let me pull up a periodic table here. You can see that boron is over here on this side of the periodic table, and that it's a metalloid. It's kind of in that range. These are non-metals over here. These are metals down here, and these are metalloids in the light green color. So what that means is that they're not particularly electronegative. In fact, they are more, H is more electronegative than B is. That's the point. So you've got the non-metals. So you've got reactive non-metals over here. Metalloids are here. So they have that delta plus on them, which effectively means that what the NaBH4 is a source of what I'm calling H minus. I'm going to close that tab down. I think it's slowing my computer down. There we go. Hopefully that will take care of it. So whenever I see NaBH4, I think of just H minus as being the reactant there. So what happens is that, again, you know, this C double bond O, we talked about this earlier with the Grignard reagent, can be expressed as being a delta minus on the O, delta plus on the C. And the H minus can come in, attack the C double bond O, and you'll see it's a very similar pattern to what we just dealt with the Grignard reagents. And there's your product there. Now you can include the H's at the end or not. Remember, these are line structures, so you're not obliged to show the H's on that C, but if you wanted to, you certainly could. But you'll see the effect here is that what was a C double bond O has been turned into an OH. And that was a double bond, and now that's a single bond. Does anybody have any questions? Okay. At this point, let me show you how best to review or study for this next test. I think some of you are going to be inclined to just kind of wait till the last minute. And actually with this test, I'm being honest, you might get away with it. There isn't that much material to learn. Maybe you will get away with just studying on the day before. It might lead to complacency later because, you know, you might get away with it this test. You certainly won't get away with it in test 3. I guarantee that. But, you know, I would say though, if you want to start getting into it, what you should do is, I've got this problems test 2 file here, which is the same as that blue book. Has anybody been able to get the blue book from the bookstore? Can somebody answer that?
Yes.
Has anybody, was that a yes?
Yes.
Yeah. Okay. How long did it take you to get it, Jacinth?
About 2 weeks.
Yeah. Yeah, I'm not very happy with the bookstore.
I got mine before, but I ordered early. So.
Yeah. Well, still, they should have had it ready and ready to go rather than make people wait for it. They're incompetent. I don't like them. All right, let's have a look. This is the, okay, so first of all, let me show you what we've got here. I've got a reaction summary, which pretty much goes through all the reactions that we have in the PowerPoint, but it shows the mechanisms as well. So that's all there. And then there's the problems here, right? So these are all a mixture of all of those different kinds of reactions. I've got 54 of them. These are answers, right, to those problems. But for the mechanisms, there's another file here, this mechanisms test 2, which goes through each of those problems and shows the full mechanism for each one. And it's one per page. So they're pretty easy to find. So the intent there is that you could possibly do those problems that start here on page 18, and then you can check your mechanisms against mine that I have in that file. So that, well, I think that'd be a good way to prepare for this test. I don't think memorizing the products is the best way of doing it, although that's the way some people will want to do it because they think it's going to be easier or they think it's going to be less time consuming. But in the end, it's not going to serve you very well. I can just say that, I think. Does anybody have any questions?
So for this test, do we need to show the product? That wouldn't be like option. The mechanism, I'm sorry.
No, you need to show the product. The mechanism will be optional.
Okay.
In the first part, but there are going to be specific mechanistic questions. We've already seen one of them. That was one of the cyclic acetal or ketals, hydrolysis or formation, Miriam. That was one of them. And we're just about to look at the second one now. Okay, so the next one is either going to be, well, the other mechanistic problem will be a primary amine addition elimination or a secondary amine addition elimination. So it'll either be H or J as it appears on this document here. Let me see, I should increase the size here as well. Okay. So first of all, let's look at what I mean by a primary amine. So primary amines have one carbon connected to the nitrogen, which means they are an NH2. A secondary has two carbons connected to the nitrogen, which makes that an NH. And a tertiary amine has three carbons connected to the nitrogen, which means there are no hydrogens on the nitrogen in a neutral form. When we have a primary amine and we react it with an aldehyde or ketone, the product we end up with is called an imine, which is this, well, when it's an alkyl group, it's called an imine. I'll give you an example of this. So this is a primary amine that we're dealing with here. And the product we end up with is an imine. Now the mechanism goes like this, and this will be one of the possible mechanisms you might see. Now, given that this is not a 1-2 kind of reaction, we are welcome to use H plus in the first step, and we should, because that's the more reactive of the two species that we're dealing with. And then the amine will react. With the N attacking the C+. Now, if you look at the product here, and if you're doing a mechanism, you'll always have the product in front of you. You'll notice there's no presence of an OH, which tells you that the O is going to be protonated so it can leave. And the best way to protonate it is by looking at what I'm calling a proton transfer. We looked at these last time when we were doing the acetals, cyclic acetals and ketals. So you'll see the effect of that is now the O that had the OH on it is now going to have a positive charge with 3 bonds. And then in the last step here, you'll see the hydrogen leaving the nitrogen and the OH group getting kicked out and forming our imine as a product. So that'll be H plus and H2O coming off there as well. All right, does anybody have any questions about that mechanism? So one of the ways, actually, no, let's move on to, we'll look at this one first. So the example I just showed you was one where you've got a certain kind of primary amine here that has an alkyl group attached to the NH2. But there's lots of other things attached to NH2s that also react, and they react in a very similar fashion, but they produce, of course, slightly different products. So if you use NH2OH, you can still see you get the C double bond N here, but the compound we get, that's hydroxylamine, by the way, that compound, we get an oxime as a product. If we use hydrazine, then we get a hydrazone as a product. Hydrazine is NH2NH2. And then if we use phenylhydrazine, it will attack at the NH2 group, generally speaking, and form what's called a phenylhydrazone. And the nitrogen that's on the end with the NH2 is a lot more exposed than the N that's in the middle here. So this N ends up being more nucleophilic, and we end up getting the hydrazone, the phenylhydrazone as a product. In the case of hydroxylamine, the N is more nucleophilic than the O. So again, it's what attacks the C double bond O and not the OH. Does anybody have any questions?
Yeah, that's kind of complicated. Are you going to go over that again at some point?
You think that's complicated? What's complicated about it, Julie?
Just that you said it so fast, and I'm looking at it and going, yeah, but how would I, like, yeah.
Well, the NH2 is what is attacking the C double bond O in every single instance. And the mechanism is exactly the same as what I've got here on this slide.
So it just depends on the end of what's attached to the N is what you're saying?
That's right.
Okay.
So, with the primary amine, that R primed that you see at the very top there was the alkyl group. It would be this 3-carbon chain that I'm circling here. What I'm trying to get you to see here is that everything that's attached to the NH2 just gets carried along.
Okay.
You with me?
Sort of.
Sort of?
Yeah, I am. It just, yeah.
But the point is, if it's got an NH2 in it, it's going to be NH2 that adds to the C double bond O and forms that C double bond N. How does it do that? It uses that very mechanism that we just went through here. But all I'm asking you to do is apply the same mechanism no matter what is attached to that nitrogen. Okay? Do you have any other questions about that, Julie?
No, I'm good, thanks.
Okay. So one of the ways that we can use this, and this is not really something that's going to be on the test, but I'm showing it here, is called reductive amination. And what that does is we form this imine, which has a C double bond N, and then this imine can be treated with hydrogen and palladium. We've seen this reaction before when we were looking at reduction of nitro groups into anilines. And what it will do is it will take a C double bond N and change it to an NH with another H. So this is a way that we can actually make amines, specifically really secondary amines, if we're being completely honest here. So as long as you start with a primary amine here, you can actually make a secondary amine with one extra step, and that is by treating that with hydrogen palladium and taking the C double bond N out and putting 2 hydrogens on it. Anybody got any questions? Okay. So we've dealt at this point with primary amines, and you can see the product of the primary amine was this C double bond N product that we've already looked at. But what happens if we use a secondary amine? You can see that the product is a little bit different. Instead of forming the C double bond N, it forms a C double bond C. So what's happening here is that when we're dealing with ketones, we have a slightly different, well, or an additional way of numbering ketones. Because generally speaking, we've got a little bit of symmetry, maybe not necessarily symmetry so much as we have carbons on each side that are similarly reactive, let's just say that, then they each have sort of names that we name after Greek letters. So the C next to the C double bond O we call the alpha C, or the alpha carbon. The one next to that we call the beta carbon, then the gamma carbon, then the delta carbon. And this just really defines the distance of a carbon or a hydrogen attached to that carbon from the C double bond O. But we usually just deal with alpha and beta, but just alpha mostly, really. Beta to a smaller degree, but alpha are the ones that we really look at. So what we're looking at here is because once we put the nitrogen on here and it loses a hydrogen, there's not another hydrogen to lose. So at this point, once we get to, let's see, this step in the mechanism where we lose a hydrogen off the nitrogen, we don't have that hydrogen to lose, so it can form that C double bond N. So what it will tend to do is take a hydrogen off a C instead and form a C double bond C instead of a C double bond N. So let's look at, we'll look at an example here. The implication is that on the ketone or aldehyde we're reacting with, we have to have a hydrogen on the adjacent carbon, which we're calling the alpha carbon. That's the alpha C right there, the one next to the C double bond O. So as long as there's a hydrogen on that, then we can get that other kind of product. So let's look at an example of that. Actually, what I might do, I'll leave this here, and I'll create a new file here. And I'll put them side by side so you can contrast them and you can see what changes as we go through the mechanism. So remember, this was all primary amines. This is now a secondary amine that we're going to be dealing with here. Now, what makes it secondary? Well, what makes it secondary is the fact that it's got 2 alkyl groups attached to the N instead of 1. So we've got an NH here and non-NH2. So the product, actually, I'm going to cheat a little bit. I'm going to make this symmetric, so I don't end up with 2 products, but I'll show you the effect of asymmetry in a second. So there's our product. You'll notice the difference in the 2 products. This one has a C double bond N, this one has a C double bond C. And remember, this is what I'm calling the alpha carbon, which has hydrogens on it. Okay, so let's look at how this goes. And then we put the H, we add the H plus to the C double bond O. That's the same thing as happened previously. We'll have the N attacking the C plus. Again, not really a surprise so far. Which puts a positive charge on the N. And then we have the O take the H. Again, we know that the OH is going to leave, so it'll take the H off that N plus. And the product is going to look like this. We'll have the H on the O plus. And then there's no hydrogen now on the nitrogen, you'll notice. We don't have this option down here, this one I'm pointing to. It doesn't do the same thing. So what happens is that one of these hydrogens that's on the C will be lost. And instead of getting a C double bond N, we get a C double bond C. So that's our product there. Does anybody have any questions so far?
So why this? I understand that in the other mechanism we don't have the hydrogen in this mechanism, and that's why the hydrogen from the carbon gets lost, and then we make a C double bond C. But why doesn't happen in the previous mechanism? Like, why couldn't it happen?
Yeah, that's a really good question. The reason is, and I was going to go over that, Miriam, but you beat me to it. The reason is because the C double bond N is a lot more stable than the C double bond C is. So given the choice, it'll much prefer to make a C double bond N than the C double bond C. But because it doesn't have that choice in the second one, it has to go with the C double bond C. But that's a short answer. Does anybody have any other questions? Okay. So when we're dealing with a symmetric ketone, that is one that's got a plane of symmetry down the center like this one does. And you can see it goes right through the C double bond O there. Then we get one product when we treat it with an amine or a secondary amine, and the double bond could be on either side. So either way, that would give you the same compound. But you'll notice if it's an asymmetric ketone, you'll end up with two products, one where the double bond is on one side and one where the double bond is on the other side. That should have another M in it. I keep on meaning to change that, but yes, that should be two M's, asymmetric. Now, if there's no alpha hydrogens, that is, there's no hydrogens on the C connected to the C double bond O, you don't get a reaction. Because we need this hydrogen here, there needs to be a hydrogen on, where are we? Let's go back to this one. There needs to be a hydrogen on this carbon here, or this carbon here, in order for it to form that C double bond C. If we can't do that, then we don't get a reaction. All right, does anybody have any questions? Okay. I just want to point out to you here what we're doing in the syllabus. I just want to make sure everybody's kind of up with everything here. I talked about this the other day as well. But I've got test 2 as being slated for Tuesday, March 1st, or March 2nd, actually, I think it is. Yeah, March 1st is the Monday. March 2nd is the Tuesday. So just be aware that, you know, we are here in the week of February 15th right now on Thursday. So we're looking at about 10 days from now as for having test 2. I mean, we'll pretty much finish most of the reactions today. Most of them will be done today. And then in the rest of the time, I'm going to be focusing on synthesis reactions and the roadmap. And also there's going to be an NMR question as well on the test, which some people are groaning about already. But some people are going, yay. Some people are going, no. All right, so just be aware of what's coming up here. All right, let's go back to where I was. Here we go, right. Okay, does anybody have any questions so far? So if we look at a test, and I guess we'll pull up an old test here, just to give you a little bit of an idea of what's going on. I have already shown you one of the questions that you'll definitely get on the test as a mechanism question. All these other ones here that I'm showing you, they're requiring a product. You ignore the names, of course, here, just like we did on the previous one. And you can get a bonus point for showing the mechanism there. So this question 3 was the one we looked at the other day, which is either a cyclic acetal or ketal formation or hydrolysis. And the other one is either going to be a primary or secondary amine addition or elimination problem. And this is what we just dealt with, which was H or J in that listing for number 2. So these are the two mechanism questions you're guaranteed to get. One that involves amines and one that involves cyclic acetals or ketals. Anybody got any questions? Okay. So let's look at the next one. This is called the Wolff-Kishner reduction. And the Wolff-Kishner reduction, what it will do is it will take an aldehyde or a ketone and turn it into what amounts an alkane. So it's a pretty extreme kind of reduction process. As the C double bond O disappears, we end up getting 2 hydrogens in its place. The mechanism is shown on the screen here, and actually give you 2 bonus points if you can get this mechanism, because it's fairly complicated. So this is something that you can do. You know how many people usually do it? Maybe about 1 or 2. It's not really worth anybody's time to learn, apparently. But if you look at the actual process, it's a fairly simplistic pattern. If we want to look at a typical, actually I'll do it up here. So if you use these specific reagents, so it's NH2, NH2, KOH, and diglyme, and 200 degrees Celsius. So that's pretty intense if we're talking about conditions here. Diglyme is a very high boiling solvent. It boils at about 200 degrees, not coincidentally. Solvent. And the product then is just going to be the alkane. I'll just put 2 hydrogens here for where the C double bond O was. Now, if you look at the mechanism, I'm not going to go through the entire mechanism here, but the driving force is this last step here, or the second to last step, where we get this nitrogen gas formed as a product. Now, nitrogen gas is a gas, and it will just float away from the reaction here. But what that means is that once it floats away, it's irreversible at that point. I mean, the reaction can't go back to the previous step here. So what will happen is nitrogen goes, and then the reaction will continue, but it has no choice but to form the product in the end. But it requires pretty harsh conditions in order to get here. Does anybody have any questions about the Wolff-Kishner reduction? So I'm telling you, you won't ever get this as a required mechanism for credit. It will be part of question 1, I guarantee that. And you will be able to get 2 points for doing the mechanism because it's a bit more complicated. But that's it. Does anybody have any questions? Anybody have any questions? The Clements and reduction is a similar reaction, except that it's done under acidic conditions. The previous one is done under very basic conditions. So if you've got something that's in the ketone that's very sensitive to base, then maybe this isn't the method you want to use in order to react it. You might want to use the Clements and reduction instead. It uses a zinc mercury amalgam. Now, an amalgam is a mixture of metals, and mercury, I think most of you know, is a liquid. So what you can do is you can take zinc and dissolve it in mercury essentially, and it creates an amalgam. Now, the other kind of amalgam you might be familiar with is the silver mercury amalgam. This used to be used for teeth fillings years ago. I don't think they use it anymore. I think most of the time when fillings get done these days, it's a kind of like a polymer type situation, or a ceramic almost, where, you know, then they hit it with some sort of UV light to bond it and do some other things. But in the olden days, about back when I was a kid, they used to use silver mercury amalgams, and those were found to be perhaps not so great because mercury has an effect. If it leached out somehow from the filling, then it could possibly affect one's brain. So that's probably not a good thing. But this is zinc mercury amalgam and HCl. So it's an acidic reduction. It's fairly harsh conditions again. but it gives the same kind of product. Does anybody have any questions about the Clements and reduction? No mechanism for this one. I'm not going to ask you this one on the test, I can guarantee it. Okay. The next one is called the Wittig reaction. And the Wittig reaction is, it's a fairly cool reaction because what it allows you to do is take a, whoops, didn't mean to do that. It allows you to take a ketone or aldehyde and turn it into an alkene. And, excuse me, it does this by virtue of something called a Wittig reagent. Now, the Wittig reagent here is made from this compound called triphenylphosphine and some sort of alkyl halide. Now, if you think about triphenylphosphine and you look at where it is in the periodic table, phosphorus is, it's in the same group as nitrogen. So it has an electron pair on a lone pair that is possibly nucleophilic, just like nitrogen is. So it has the possibility to react with an alkane with a bromine group on it. So this would be an example of that. So pH, do it down here, pH. pH is the phenyl group or the aromatic ring, right? So that can react and form this kind of compound. Oops. Now the phosphorus has 4 bonds on it, which puts a positive charge, and the Br will be negative here. And then what can happen is we can treat this with a very strong base, and the strong base we use here is called N-butyllithium, and it will take a hydrogen off this carbon specifically here. And the reason it removes this hydrogen is because the anion it gets is stabilized by the positive charge on the P next to it. And this is actually in resonance with this, which is called the Wittig reagent. The N-butyllithium, let me talk about what that is. I said it was a very strong base. It's not very much fun to work with, I can tell you that. What it is, it's a butyl group with a lithium on the end, like this. And what happens is it will take hydrogens away from something, pretty much anything really, anything that is even slightly acidic. And we'll say AH. And it will form butane plus A minus. Now butane is a gas and it will float away, but you know, it's also flammable, right? I mean, it's the component in butane lighters. Now I know when you look at a lighter, you look at it and you see the liquid in the lighter and it's butane, but it's butane that's under pressure. So when you put butane under pressure, it turns into a liquid. But when it's, in order to light it up, you know, you hit the thing on top of the lighter, the flint, and it will release the butane as a gas once it hits the atmosphere, and then that can be lit up, and that's what creates a flame in the lighter. So you know, it's a pretty dangerous thing to work with, especially when you hit it with water, because water is fairly acidic, or acidic enough to react with N-butyllithium. All right, does anybody have any questions? Okay, so that's how we get the Wittig reagent. The fun part is how the Wittig reagent reacts with the aldehyde or ketone that we're dealing with. Oops. So let's say we had this ketone and we reacted it with the the Wittig reagent we just made. Then the product is going to be this. And I'm hoping you can see the pattern. I'll circle this group here attached to the, let's see, 1, 2, oops. Here we go. So that's the group that's attached to the triphenylphosphine, and then you've got this group here, which I'll put in a square. And that's the group that's part of the ketone. The other product we get is called triphenylphosphine oxide. And P double bond O's are very stable. And that's what drives the reaction here. So let's take a look at the mechanism, which I think is kind of a fun mechanism. Not sure everybody agrees, but I think it's fun. So I'll leave this over here and I'll just show you the mechanism here. So what happens is that we know that the O on the C double bond O is delta minus. We know that the C attached to it is delta plus. We also know from the situation we have over here with the positive and negative in the resonance structure, that the delta plus is on the P and the delta minus is on the C. I probably didn't draw that correctly. I'm going to flip this around because it's going to make it a little bit easier for me to show you this. I meant to draw it flipped around rather than the way I did do it. Okay, let's try that instead. So that's going to be delta minus on the C, delta plus on the P. And what happens is that the mechanism goes something like this. And we end up getting this, it's called a phosphoccitain, but it's a 4-membered ring with oxygen and phosphorus in it, essentially. I might put that in over a little bit here so I don't run out of room. And then what happens is it falls apart in the opposite direction. And we end up getting our products, which are the alkene plus the, actually I won't put a plus there, and the pH3P with the double bonded oxygen. Does anybody have any questions?
Yes.
Yeah.
So phosphor that is attached to those 3 phenyl, to those 3 benzene group, is a delta positive. Isn't that the oxygen attacks that? So like, why the arrow is the other way? Shouldn't it be should we show the direction of movement of electrons? Electron comes from the oxygen attack that positive charge phosphor. No? You know where I'm pointing?
Oh, well, yeah, I kind of see it. Yeah, you know, yeah, I think you might be right. You can. It's not that it's completely wrong what I'm doing, but it's not. You're probably right. What you're saying is probably a bit more correct, Miriam. So I will adjust that. Yeah, I'll say it. All right, all right. Yeah, it's you're probably right. I will change the arrow direction here. It's not that if you did it on the test, I'd be fine with it though, to be honest.
Okay. Okay.
But let me switch that around. I think it's probably a bit more correct to say that. I think you're right. So what you're arguing here, and you'd be correct. The arrow should be more like this, right? And like this.
Yes, because
Yeah.
yeah,
Yeah.
yeah.
Yeah, that's fine, because then you are really showing more of the electron movement than anything else. So yeah, that'll work too. But either way, if somebody did it the other way with the arrows, I'd be fine with it. All right. Anybody got any other questions about the Wittig reaction? Now on the test, I don't show this part with the Wittig reagent. I just show the reaction of the Wittig reagent with the, I'm looking for a product of the Wittig reagent with the ketone, not this first part here. So you don't have to worry about that being on the test. At least not that first part anyway. But you will definitely get a Wittig reaction on the test. There's no question about that. So as you can see, there's only a couple of these reactions left. The next one is called alpha halogenation. And you can see that the end product here has a halogen on the alpha position, that is the position next to C double bond O. So let's see how this works. So what happens is if you've got a C double bond O, it's actually in equilibrium with another form of a ketone called an enol. There we go. So that's the keto form. This is called the enol form. So whenever you've got a bottle of ketone, maybe less than 1% of it will be enol because it's interacting. Now the actual way that we can get this is the O takes the H on the adjacent carbon and turns it into the enol. Now the enol is a whole lot more reactive than the ketone is. Now that reacts with the bromine. We can end up getting the OH here with the bromine connected, but that leaves a positive charge. That leaves a positive charge on the C that's under the O, which can lose an H plus and turn into the ketone again. Which is how we end up getting this product. Now, one thing about this process, I told you that the enol is only in very small amounts. But what happens is, by Le Chatelier's principle, the bromine will react with only the enol, but as soon as it reacts, more enol gets formed. So the keto is always turning back into enol, and then we end up getting it reacting with the bromine, and we end up getting it pulled through all the way to the products. Does anybody have any questions about alpha halogenation? Okay. One of the more complicated reactions, and this is kind of a good segue into what we're going to do in test 3, which is reactions of carboxylic acids. We see something here that we don't normally see with aldehydes and ketones. All the reactions we've dealt with here have never shown this kind of step that we see in the middle right here, where I've got the cursor pointing, where the O- comes in and kicks out a leaving group. We have never seen that here in any of these reactions. That's because aldehydes and ketones have H's or C's, and these are terrible leaving groups as negatives. So CH3 negative, H negative are awful leaving groups. But if we can make some sort of adjustment, then maybe we can make that happen. So the way that this works is that we start off with a methyl ketone. And by methyl ketone, I'm talking about a ketone that has a methyl group on one side of it. So that's a CH3, which makes it a methyl ketone. The other thing we know is that if we were to react a methyl ketone with a base like sodium hydroxide, it is possible for the sodium hydroxide to pull off a hydrogen. And you'll notice that this is an alpha hydrogen as well, because it's right next to the C double bond O. Because what that does is it forms a negative charge that can resonate between the C and the O, the double bond O here, which gives it a little bit of stability, that anion. So what we know is that alpha hydrogens are somewhat, well, we say they're somewhat acidic. And they do this because there is a somewhat stable anion formed. We've talked about this before with regard to acidity. So the bottom line, though, is that that hydrogen next to the C double bond O, specifically the one on the methyl group, and because it's more exposed, is somewhat acidic. And what that means is it can be replaced by an iodine, which is what we're doing here. If we do this 3 times, we end up getting this kind of creature. Which has 3 I's attached to that C that's adjacent to the C double bond O. So you just understand we've done this 3 times now. Does anybody have any questions? Now you'll notice that this I is a big element. It's a massive atom. And what that does is it makes this a very long bond. And because it's a long bond, it's a weak bond too. Which means it's easily broken. So what that means is, when I've got this compound with the 3 I's on it, the OH minus can actually come in. The electrons go up on the oxygen, which is what we'd expect, but what you might not expect is that this O negative will come down and kick out this thing with the 3 I's as a leaving group, which it will only do because that bond there is long and weak, which is why we end up getting the carboxylic acid here plus this leaving group. The problem is this negative charge is very unstable, so it will take the hydrogen off the acid group, which is by its very nature acidic, and produce the anion, and this compound, which is called iodoform, smelly yellow compound, melts at 119 degrees or something like that. And you get this anion, but because you've got the negative charge there, then in the last step we can add H plus to it, and that will form a carboxylic acid. So the end product ends up being this carboxylic acid that I've got down here. So it would be, I'll go ahead and show that. So the H plus is what gets added in that next step, and we end up getting that carboxylic acid as a product as well. So the upshot of this is that if you've got a methyl ketone, then you can get this iodoform form, this yellow solid here. And this can actually be a way that you can use to test for methyl ketones. So if you do this reaction on a ketone and it forms a yellow solid, you know it's a methyl ketone. If it forms a kind of like a yellowish liquid, then it's not a methyl ketone, it's some other kind of ketone. So that's what we're looking at. That's what the iodoform reaction does. But its main purpose here is to form a carboxylic acid. All right, let me also say something about the products expected on the test here. Anything that's got carbons in it would be expected as products. So what that means is that if I'm looking for this reaction, this is also a product, the iodoform. And likewise, in the Wittig reaction, the PH3PO also has carbons in it. I'm also expecting to see that as a product as well. So that's something to watch out for. The Cannizzaro reaction won't be on the test, and if you want to read about it, you can, but I'm not going to put it on the test. All right, so in the last 5 minutes or so, let me go through and tell you exactly what you will see on the test. Let's see, did I do it? And I didn't download it. All right. Let's download it. I hope this won't take any more than a few minutes, but it might. So just bear with me if I go over a little bit, okay? I try not to go over, but sometimes I do. So reactions you're going to see, this is just for number 1, right? come on. My computer's slowing down a little bit here. We'll have alpha bromination. That'll be one reaction you'll definitely get. Remember, there's no naming. There'll be no naming on the test, okay? Come on. What happened? Why is that not coming up? Oh, there it is. I don't know what happened there. Iodoform reaction, you'll definitely get that as well. What else will you get? The Wolff-Kishner. Let's see what else. Possibly an oxidation. Or remaining, there might be a remaining reaction at the end that is not. I'll talk about that in a second. Okay. Acetal or hemiacetal. Or ketal or hemiketal. Primary or secondary amine elimination. Addition elimination, I guess I called it. A Wittig reaction. A reduction. NaBH4. Okay, okay, so let's just say 2 by primary, secondary, addition elimination. Then a Grignard reaction as well. And that's it. Okay, so that's for number 1. So you've got them pretty much, when I say remaining reaction here, whatever isn't on this list, and look at reaction summary. I don't know what that reaction might be, but look at the reaction summary. I'm just covering myself here. And that's in the blue book, obviously, I'm talking about. We looked at that earlier. So you can look at that, and you can look at the old tests, and you can see what kinds of things have been looked at in the past with question 1, but that now gives you no excuse. You can start studying the reactions. Right, so you've got 10 days or so, or 9 days until the next test. So now you can start studying. Nobody can say, oh, well, he hasn't been through all the material yet. Yeah, I have now. So you can start looking at it. I showed you earlier what you should do as far as studying goes. Okay, so I'll leave it there for today, and we'll talk more on Tuesday.
Can I ask you a question?
Yeah.
When you say remaining in reaction, it's still not going to be any of the ones that you said were definitely not on the test, right?
Right.
Okay.
That's true. If I went through and showed you like the Cannizzaro or the, what was the other one? Do you remember?
I don't know. There was one.
Oh, that's right. Reductive amination was the other one. Yeah. So yeah, I wouldn't count on, you won't see those on the test, either of those.
You won't see them. Okay.
No, not those.
Thank you.
All right, no worries. I'll see you all later.
Have a great weekend.
You too. Thanks. Bye-bye. Jasmine, did you need anything from me?